Welcome to Unlock Layouts. In today's video, we are going to discuss 16nm and as well as 28nm base level layers and as well as the layout comparison. So let's start the video.
So what we have here in the left side, so this is our 16 nanometer technology inverter design. So what we have in the right side, this is our 28 nanometer technology inverter design. So let me open the device properties for you. So right now we have a low voltage device, so which is nothing but P channel LVT device. So LVT states that it's a low voltage device. So this is like what we have here. This is our 16 nanometer design. In 16 nanometer design, only the LVT device having the lowest gate length of 16 nanometer. If suppose if you are going high VT device or SVT device or some other intermediate voltage device, then the gate voltage is not it's a 16 nanometer, so it will be vary. Okay, it won't be under 16 nanometer, it will be always higher than the lowest nanometer. So that is nothing but our 16. Okay, so only LVT devices, they are using the lowest gate length of 16 nanometer. Okay, so we'll discuss about the 28 nanometer design also. Even we have a 28 nanometer TSMC foundry. This is also P channel LVT device. Here, even though it is a 28 nanometer design, the lowest gate length as possible is 30 nanometer, because maybe 28 nanometer gate length they are using for the standard cell design, but you know, analog cell design, even though if it is a 28 nanometer, the lowest gate fabrication size is 30 nanometer. And then apart from that, we have our finger width and other width and fingers and multiplier, all the things are same. I hope most of the people are aware about this 28 nanometer design, but FinFET is the latest cutting edge technology. So here we have only some extra options in the parameter, that is nothing but our fin. So here I have mentioned the fin numbers are 5 and then the finger numbers are 2. Fingers we can vary the size, and as well as the fin numbers also we can vary according to the designer's wish, and according to their design the fin numbers and finger values will be vary. Okay, it will be more than 2 or lesser than 2, it depends on their design. And then apart from this fin, most of the DRCs will work in the layout related parameters only. So in this layout related parameters are too much important to us in the P cell design and as well as the analog design. So in 16 nanometer TSMC foundry, they have left port and right port. So left port and right port is like extra one more layer. So I'll explain these left port and right port in the layout point of view. So as of now, we'll discuss these things in a schematic. We have a left port and right port. If you want, we can enable and disable these by selecting these option. And then apart from that, whatever it is there, left dummy, right dummy, primary dummy, secondary dummy, everything will be available in even 28 nanometer also. These options are available. So dummy will be fabricated from 28 nanometer. Okay, so from the 28 nanometer technology, they are started using dummy poly. So primary dummy and secondary dummy, the same technique they are using for FinFET also. So this left port and right port is like additional one more layers in our 16 nanometer TSMC FinFET design. And then apart from that, we have left contact, right contact, and as well as the swap of source and drain terminal. Everything is remains same. Even these options are available in even in planar MOSFETs also, and even this is same for 28 nanometer also. But you know, apart from that, some other options are there. So here we have some option called contact type. Whether if you want, we can go for a square contact. Suppose if you want a rectangular contact, then you can go for rectangular contact. So these things are completely up to the designer wish and layout engineer wish. So whatever the convenient type for the contacts, either it's a square or rectangular, we have option to choose in 16 nanometer. But you know, in 28 nanometer planar MOSFET, we don't have this option. So this contact via, so these contacts are nothing but OD to poly and then poly to M1. So these base level contacts, whatever we have options to choose whether square or rectangular. But in normal planar MOSFET, we don't have that option. And then most of the layers are almost same, but you know, like we have some extra implanted layers also. We have extra some layers are there, like LBS dummy layer. So these layers are not present in 28 nanometer. And then fin boundary, if you turn on this fin boundary, then the fin boundary will be visible. Fin boundary is nothing but one more layer. It's like a straight line. Okay, so let me show you these things in the practical layout. And then we have a CPO layer here. I don't know what is this CPO layer. If anybody aware of this CPO and CMD layer, who has worked in the FinFET technology notes, just comment this layer functionality and layer usage in the description box or comment box. Even I don't have much experience in FinFET, so I don't have idea about the CPO layer and as well as CMD layer. Okay, so then apart from that, I don't think so, nothing major difference is there here, but these are all the schematic properties which is related to 16 nanometer and as well as what we have right side is our 28 nanometer. Okay, so let me generate the layout for you to understand in a better way. So as we discussed earlier, I have generated the P MOSFET and N MOSFET device from the same schematic. So hope the right side whatever we have here, this is our planar MOSFET, which is nothing but 28 nanometer TSMC foundry, and left side what we have, this is the P MOSFET and as well as N MOSFET. So this is nothing but our FinFET design. So you can able to see some straight lines here. So these straight lines are available only in the FinFET technological node. So this is like fin boundary layers. So this is like fin boundary layers are there in the FinFET design. Okay, so this fin boundaries will be continuous entire the layout. Even though if you are placing your device, if you are not placing your device, that doesn't matter. Everywhere from the design. Okay, so every empty spaces, wherever the empty spaces are there, this fin boundary will be continuous. So let me enable these devices by one. So see here in our 28 nanometer technology, whatever it is there in the right side, if you generated the device from the layout, so by default you are getting this primary and secondary dummy polys. But you know, in the FinFET device, generally these options will be in the disable mode. So suppose if you want to change the device properties or if you want to enable those primaries and secondary dummy, just select this device and go to the property of this device. Okay, so I am going to select all the device. Okay, let me select by one. I am just going to select the first N MOSFET device. So just go to the layout related parameters, just turn it on, and then see here it's completely turned off, left dummy and right dummy. So if you want, you can turn it on. If you don't want, then let it be in off stage only. Okay, so it's completely up to the designer wish. See, so you can able to see the dummy layer, left dummy and right dummy. See, in this 28 nanometer technology, we have to discuss about the C-pod layer. Okay, so in 28 nanometer technology, we don't have C-pod layer, but we have to understand what is exactly C-pod layer. So here, this device parameter, let me open the device parameter. So this device parameters, number of fingers is 2 and the number of multiplier is also 2. Okay, so we can change this device parameters if needed, but as of now, the number of fingers values are 2. So as we know, so this is our first finger, whatever it is there, this is our first finger and this is our second finger. So we don't have any other extra poly layer here, only we have the gate length of, this is our first finger and this is our second finger with the gate length of 13 nanometer. And since it is a 2 finger device, we have a source terminal here and then we have one more drain terminal and then again we have one more source terminal. So followed by the source terminal, our primary dummy and secondary dummies are available here. If you go to the FinFET device, just I'll go and I'll click the FinFET device and I'll take a parameter. See here, left pod and right pod is turned on, but you know the device parameter is, it's a single finger device. Okay, it's a single finger device and number of fins are 5. So let me show you where the fingers are there and where the fins are there. In this layout, you can easily able to identify where the fin layers will be available and then where the finger layers will be available. Let me close and show you. Fine. So we have a gate layer here. So this is our single finger gate device. Okay, this is a single finger. This is our active gate, and left and right we have a same poly layer. So even though instead of keeping dummy poly, generally we used to protect that poly from the itching and then the process variation point of view. If you want to protect the poly, then we need the primary dummy and secondary dummy. But you know, like this primary dummy and secondary dummy will be okay for 28 nanometer planar. But you know, when you come to the lowest technology node like 16, even though if you have a primary and secondary dummy here, of course we have a primary and secondary dummy here, even though we have a primary dummy and secondary poly dummy, we have a one more layer called a C-pod layer. C-pod layer also has to be there in the left and right corner of all the matching boundaries. Since it is an inverter, I am just keeping my C-pod layer as it is, but if you want to merge multiple number of fingers and multiple number of multipliers, then the C-pod and as well as the secondary poly and dummy poly, whatever the dummy polys are, it should be there on the left and right boundary. So that's the minimum DRC and that's the foundry rule. See, right now I have disabled all the layers. I have just enabled only OD layer. Okay, oxide diffusion is our OD. See, just this is our OD. just count how many fins are there in between these OD. So from here to here, see 1, 2, 3, 4, 5. So this is nothing but our fin. FinFET fabrication is completely in the 3D view, but we are not working in the 3D layout. Okay, we are just working in the 2D point of view. Okay, so even though it's FinFET, we are working in a 2-dimensional view, not in the 3-dimensional view, because 3-dimensional fabrication layout is not possible with CAD and Virtuoso. Okay, so if you want to calculate how many fins are there, how many fins are available in the layout, just see how many fins are available within the OD. So this is a 5-fin device. Let me change the device parameter for your better understanding. Instead of keeping 5, now I am going to change this as a 10-fin and as well as 2-finger device. So this is just for understanding purpose. Okay, let me apply and then see the device parameter. See, now before we have a 5 fins, but again if I change the parameter from the layout, see one more 5 fins are increased. So totally right now we have 10 fingers within this exact OD. So this is nothing but our FinFET design. And as well as what we have changed 2 fingers also. Let me enable the poly layer. See, before we have a single finger, I think top side, this is our PMOS. So just compare our design with respect to our PMOS. So if you are keeping a single finger, then we have only single finger here. So this is nothing but our active gate. So whatever it is there in the middle, this is our active gate. Left and right we have a C-pod layer, that is left C-pod and right C-pod. Suppose if I converted into 2-finger device, instead of 5 fins, I am trying to convert this as a 10-fin and as well as 2-fingered device. Okay, so if you convert this 2-finger device, see this is our first finger and this is our second finger. By default we used to get the left pod and right pod. So this is nothing but our C-pod layer. So C-pod layer is also mandatory to prevent the fabricational process from the etching related issues, and as well as we have multiple systematic and random mismatches are there, okay, with respect to poly and with respect to OD. So in order to prevent all those errors, right, so we need the C-pod layer. So this is mandatory. And then like here also I have not enabled secondary dummy poly, I think so. Let me enable this. Okay, let me turn on the layout related parameters. I think, yeah, see secondary dummy polys, I think it's turned off. Let me turn on here, apply and okay. See, yeah, whatever the designs are there here in the planar MOSFET with respect to the 28 design, same layers are available. So we don't have extra layers are there. See, the layers are clearly visible in the LSW window. Okay, if you want any reference, you can take the layer reference from the LSW window. All the base layers are same, and we have some extra layers which is nothing but our MO2 OD. So in FinFET design we have one more layer called MO2 OD. So this is nothing but they are creating some contact between OD layer to M1 layer. That's all. This is our base level contact, MO contact. But when you come to the planar MOSFET, we don't have a contact or via called M0. Directly we used to start everything from the M1 layer. Okay, so in here we used to call the layer called CO. CO is nothing but our contact which can creating the contact between OD to M1. But when you come to the FinFET device, instead of using CO, they are using MOOD. So MOOD is nothing but our CO layer. The CO layer is nothing but our contact layer. So which can creating the contact between the base level layers. So base level layers are nothing but poly OD. Okay, these are all our base level layers. Okay, so instead of calling this as a CO layer in FinFET design, they are calling this as a MOOD layer. That's all. No other difference are there. Okay, and then we have one more layer called via 0. So let me show you where the via zeros are there. See, the via zeros are available here. Okay, so let me enable M1 also. See, via 0 is nothing but this is the via which is creating the contact between OD to source. Okay, so we have oxide diffusion here. From the oxide diffusion we have to give the source connection and as well as drain connection. So this via 0 is creating the contact between the OD layer and as well as source layer. But when you come to the normal planar MOSFET, whatever vias are there here, we generally called that as a contact. So there is no via 0 available in planar MOSFET. But FinFET device we have a via 0, and as well as see we have a M0 to OD layer. So this M0 to OD layer is also available here in the same place where the source and drain terminal is there. So they are creating this MD to OD layer. Because I am not very sure about how this MO to OD layer will be fabricated in the 3-dimensional view of FinFET. I think this is a kind of passivation layer or not, but I am not very sure about that. But these layers are present here. Suppose if anybody know about this layer operation and how the layers are fabricated and how the layers will be present in the real-time FinFET 3D structure, if anybody know that, just comment in the below comment box, okay, because I am not aware of these details since I don't have experience in FinFET. So let me enable all visible layer. So apart from that, most of the layers are same. So whatever, if you go to any FinFET device or if you go to any planar MOSFET device, okay, so almost the device layers and everything is same. So we don't see any difference here, but you know, DRCs are totally different here, okay. So we have a completely different DRC here. And also I wanted to show you few things with respect to the guard-ring, okay. So right now what I'm going to do, I'm going to create a guard-ring for our P channel MOSFET. So generally what we will do, if you want to create some guard-ring here, just we'll select the device, we'll go to the shortcut for shift G. So we'll get this option, whether you want to go for N channel ring or P channel ring. Since it is a PMOS, I wanted to go as a N channel ring. I'm taking this as a rectilinear. The enclosures I am taking 0.16. So this is the minimum DRC, okay. So I'm just keeping this 0.16, okay, then hide. So here in our planar MOSFET, so we have only OD layer and as well as M1 layer. So hope you can able to see here, the guard ring consists only with the OD layer, okay. So we don't have any poly in the guard ring. But if you come to a FinFET device, you know, like this is our FinFET device, whatever I have here, this is our FinFET device. Let me clear the markers. This is our FinFET device. Suppose if I want to create guard ring for this FinFET device, just I wanted to go to the create option. See, I don't have multipath and I don't have MPP guard ring. I don't have script for this, okay. I wanted to create some particular script if I want to run multipath and as well as this MPP. So I am going to take as a fluid guard ring. Fluid guard ring is also similar kind of guard ring. Instead of going for the shift G, I am just going for a fluid guard ring. So what I am going to do, I am going to create a rectangular or path or polygon, whatever it is. We have multiple options, we can take it here. So this is a PMOS device, okay. What we have to do, we have a multiple guard rings here. So we have a GR is nothing but our guard ring, and NVEL is nothing but our NVEL guard ring. Suppose if you want a different type of guard ring which is added with CPO layer, I don't know what is CPO layer, I need to refer the DRM. Suppose if you want any guard ring with CPO layer, you have to choose the second option. And then we have a separate ring for RF device also. So this is like N channel MOSFET ring for RF device and P channel ring for the RF device. Since my device is not a RF device, I'm just taking the normal NVEL device, okay. This is my normal NVEL device. So what I'm going to do, I'm going to take as a path, okay. So instead of wrap, I'm going to take it as a path. Path is also nothing but a normal ring only, okay. So I'm going to take this and then see create fin boundary. So in this guard ring option, we have some options here. Fin boundary and create M1. If you want M1, you can turn it on. If you don't want M1, you can turn it off. And then VT layer. If you want VT layer, just turn it on. What kind of VT you want? OD18 is like 1.8 volt device. So VTH-N and VTL-N and VTUL-N. So these are all nothing but an extra implantation layer. See, I have uploaded about these layers details, and the layer functionality is in our one more video. I think in our previous video I have uploaded everything. If you want any details about this VTH and as well as this OD18 and other details, just refer my previous video. Hope you can able to get some idea about this, okay. So this is nothing but the one more implantation layer kind of things, okay. Nothing important is here. If you want, you can add this layer. Since I don't want this, I'll just keep it off. See here also we have a number of fingers, okay. Number of fingers, how many fingers you want? You want 2 fingers or you want 3 fingers? I don't know how they are defining, how they are choosing the number of fingers here. Let it be the default numbers, okay. Let it be number 2 and let it be number 3. Number of fins, even guard rings are also available with fin boundaries and fin layers, okay. So number of fins available here are 3, okay. Let me hide and let me draw some layers here. See, this is my guard ring structure, okay. So this is my guard ring structure. See, in our normal planar MOSFET, the guard ring consists only with OD and as well as M1 and as well as the base level contact. The contact is nothing but which can creating the contact between OD to M1. But you know, when you design a guard ring for FinFET device, see, already the guard ring is also consist of poly and as well as, you know, like other layers is also there. Like see here, you can able to see some one more layer, MO2 poly. I don't know what is M02 poly. I think this is creating some special contacts between poly to MO. I don't know where the MO is there. Okay, so MO is nothing but this yellow color layer. I don't know what is the functionality of this MO. Okay, MO layer is creating some contact or some isolation layers or something like that. This is creating some contacts or some layers between MO to poly. So let me enable poly. See, we have a poly here, but in planar MOSFET generally we don't use poly for gathering. Gathering will be consist only of OD and then M1, but FinFET designs are completely different. Okay, so FinFET design is completely a different design, even though a gathering are consist of poly. So we can consider this as a device. Okay, instead of calling this as a gathering, see here we have a OD and we have a poly and we have all the layers. So we can say this is also a device, but this is acting as a dummy device. So it's a kind of device, so which is creating contact. This is also acting as a gathering, and also this is kind of a device only. Okay, because poly is also there and OD is also there, and as well as M1 is also there. See, M1 layer is also there, and as well as see we have some other layers is also there. Okay, see, NVEL is there, and as well as OD is there. OD 18 is available because since it is a 1.8 volt device, so OD 18 is there, and then C pod. Okay, C pod, see, hope you can able to see the difference. If I enable C pod, see some layers are enabling here. So this is nothing but C pod dummy layer. Okay, only for they are using for dummy purpose, C pod. And then see one more PO dummy is there, which is nothing but our poly dummy. Okay, poly dummy layer is not available in our gathering. Okay, only port dummy is available, port dummy. Okay, see port dummy, hope you can able to see the difference here. So port dummies are available, and P implantation layer and other layers are base layer. So these much difference are available in FinFET design. So just imagine how the design would be difficult. So I think if the peoples are working from the planar MOSFET, if they're shifting to planar to FinFET, I think minimum 15 to 20 days is required. Okay, the minimum 20 days to 15 days is required to understand the layer functionalities, and as well as the base level DRCs and all those things, because this is completely new design and this is completely a new technology. Okay, let me run the DRC for you and let me show you the DRC status. So I'm just going to run DRC in the real-time window. So let it be window, and I'll just run in the real-time DRC. Yes, we got the results of DRC. See how many DRCs are there. There are multiple DRCs which is reflecting here. Let me show you here. So see, this is our executed DRC results. See these G1 whatever it is there, this is like a grid DRC. Okay, so this can be easily clearable. Apart from that, I think we have so many DRCs like NVEL area and NVEL enclosures, OD area, and as well as OD enclosures, poly area. See, we have so many DRCs are here. Okay, so just this is a single inverter. Okay, this is not a complex design at all. It's a normal single inverter. Like we have not completely done this layout, so this is just for a trial and error purpose and just for educational purpose I am showing. If you did the proper layout, then you may get rid of all those DRCs. The minimum DRCs maybe you will get, but just I wanted to show you the DRC results here. Okay, so let me close the DRCs and let me clear the DRCs, and I'll minimize this, and then better I'll run DRC for this planar MOSFETs also. Let me run the real-time DRC. Yeah, we got the results. Let RV should open. See, I think here also we have so many DRCs, but in planar we can easily clear those DRCs. Let it open. Yes, see here we have a latch up issue because this bottom device is not connected to gathering, and then the top device also properly not connected to gathering, so that's why we are getting that latch up DRCs. Okay, so let me open the real-time window for you. See, we have latch up and contact spacing issues, M1 enclosures, NVEL enclosures, OD enclosures. Yeah, we have multiple DRCs, but these DRCs I have very familiar with this. I think within 15 to 20 minutes I can able to clear all those DRCs because these DRCs are very familiar to me. But but FinFET device DRCs, even I don't have any idea about those DRCs. I wanted to check everything one by one, and then I wanted to clear everything one by one. Okay, so Hope you can understand this design perspective and as well as the layer wise explanation about the FinFET and as well as the planar MOSFET device. Okay, so both 28 and 16 is like cutting edge technologies. Most of the companies are using these technologies. Okay, so maybe this video will help for the freshers, so who are all willing to join or who are all willing to enter in the VLSI domain. So this minimal information will be sufficient to the freshers. Okay, thank you friends. I'll meet you soon with one more new video. I hope I have given some valuable information to you in this video. Thank you for watching my video. If you like this video, please click like button and share this video to your friends. For more details about this video, please contact us to my email ID and follow us on my Facebook page and Twitter page, and kindly subscribe our channel and don't forget to click the bell button.